There is a set of vectors that's particularly important for physical applications, and this is called the Frenet frame. The Frenet frame consists of three special vectors. The first is the so-called unit tangent vector. And the unit tangent vector, first off, this is a tangent vector, so I'm going to take the derivative of my curve, but it's going to be a unit tangent vector. So after taking this derivative, we divide by its length to ensure it's a unit vector. So in some sense, if we have a curve moving along like this, the tangent vector tells us that the curve is heading in this direction. It's the one that's running parallel tangent to the curve. Next up, we have got the principal unit normal vector. So the principal unit normal. Now, we have several words here. First, is the idea of a normal vector. So a normal vector must be perpendicular to the curve. So it's got to be heading in this direction, perpendicular, or this direction. So that takes care of the normal part. Unit means the thing must have length 1, so we've got to scale this back so its length is 1. But then the word principal tells us there's got to be some uniform choice that we always take. And we'll define this as the normal vector is pointing in the direction the curve is turning. So between these two choices, the curve is turning to the left, so I'm going to choose the vector that's pointing on the left-hand side. So that's where this principal part comes in. The way this is defined is similar to unit tangent vector, but it's the derivative of the unit tangent vector. And then to ensure it's a unit, we divide this by its length. So that's our principal unit normal vector. And the third part of the Frenet frame is the so-called binormal vector. Now the binormal vector doesn't involve any derivatives. We've done all our derivatives already. This is just a unit tangent across the principal unit normal vector. Let's look at an example of this. Let's say we've got our position is on some circle, a cosine omega t, a sine omega t, and then at some height b. So to get the unit tangent vector, we're going to need r prime. So we go through and take the derivative component-wise. We get negative a omega sine omega t, and then the derivative of the second component is a omega cosine omega t, and then the derivative of b is constant, so its derivative is 0. So that says the unit tangent vector, well, that's r prime divided by its length. So if we go through and get the magnitude of r prime, we take the square root of the sum of the squares of the components, and we've got a squared omega squared sine squared plus a squared omega squared cosine squared plus 0. Now these both have an a omega in common, a squared omega squared in common, so we can take that right out of the radical. And then what's left over is sine squared omega t plus cosine squared omega t, which is 1. So we get a omega for our norm of r prime. So if we just divide that out, we get that the unit tangent vector is r prime divided by its length, and this is negative sine omega t cosine omega t 0. So now the principal unit normal vector, we take the derivative again. So let's over to the side take the derivative of t, and this is negative omega cosine omega t and negative omega sine omega t. And then we go through and calculate its length also, because this is the second part of the formula for the normal. So we take the square root of the sum of the squares of the components. We have omega squared cosine squared omega t plus omega squared sine squared omega t. And again, we can factor out that omega squared and bring it right out of the radical. And then what's left over is cosine squared plus sine squared, which is 1. So we wind up with just omega as our norm of t prime. So we divide t prime by its length, and we get negative cosine omega t sine omega t 0. I left out the 0 over here, but that's the third component. And now to get the binormal vector. Binormal vector, we take the cross product of these two. So let's go through and set up the cross product. We've got I, j, and k. The first line in here is the first vector, sine omega t cosine omega t 0. The bottom line is the second vector, negative cosine omega t sine omega t 0. We go through and do this cross product. We've got I times this 2 by 2, which is 0 times 0, minus j times this 2 by 2, which is 0 minus 0, plus k times this 2 by 2, which is negative sine squared minus negative cosine squared. So this is negative sine squared omega t plus cosine squared omega t. And we write this out, so this gives us 0, 0, and then cosine squared minus sine squared. That's our binormal vector. So with those three, after those three vectors have been defined, we can look at the tangential and normal components of acceleration. So the idea here is this acceleration, if we're moving along a curve, the acceleration, part of it will be in the tangent direction and part of it will be in the normal direction. So this acceleration, we can decompose this as the component in the tangent direction plus the component in the normal direction. Now to figure out what these two components are, we can use the fact that the tangent and the normal are perpendicular to one another. If we dot product both sides of this equation by t, we get a dot t. And if we dot this with t, we get 1 because the length of t is 1. And if we dot this with t, we get 0 because the n and the t are perpendicular to one another. So this tells us that at is a dot t. And likewise, if we dot both sides of this equation by n, we get a dot n equals, we dot this with n and it zeroes out. We dot this with n and n dot n is 1. So this gives us a formula for the tangential component of acceleration and for the normal component of acceleration.